This project is going to see if I can interface my ZX81 to a Raspberry Pi Pico so that I can print without owning a ZX81 printer, because I don't have one. Pi Pico runs fast enough to be able to read the logic levels on the edge connector, and so it should be fairly simple to get it to recognize the I/O request. The ZX printer had a fairly simple interface. I'm not sure how many pins it used, but I think probably just used the data pins, the I/O request pin, and a couple of address pins. That's all it needs. Yeah, so that's what this project is going to be about. The board that I've used to interface to the Pico, the one that sticks onto the edge connector, it came from another project that I'd worked on a long time ago. It's still got lots of chips on it, which are no longer being used. So it looks a bit, it looks a bit of a mess. So I'm calling this the Franken printer. And before going into some of the details, I'll just load up the assembler program that I'm going to test this with, and show you where I'm at so far. So this is the ZX81 communicating with an AY soundboard. So you can see the ZX81 communicates to the Pico through the expansion port, and then via USB to a Python program on Windows, and then that Python program communicates via USB to my AY soundboard. So it's actually playing the sound effects from the Quicksilver Defender game. There's no tricks here. It's taking the memory writes to the two addresses that the ZX81 Quicksilver sound card uses as a port. That's XFF, 7FFF and 7FFE, and then just communicating all of that information via the USB cables to the AY machine, as if it was just connected straight to the back of the ZX81. Although I've not completed the creation of the PCB, I think the schematic I've got here is just about correct. So I've got all the control lines that I need. I don't actually need the clock signal, but I've got it connected at the moment, connected here to gpio 10. But I think in future I'm going to take the clock off gpio 10 and connect A14 instead, but we'll see. I think that's probably what I'll do, but we'll see. So this uses just about every pin that the Raspberry Pi Pico has available to us, all the GPIO pins. There are a couple of more GPIO pins that we could use. There's a pin for the LED, which is available with a small amount of modification, and there's one more of the GPIO pins that's available as well. Again, with a small amount of modification. It's a bit fiddly, but so far I'm getting by okay. There's a possibility of putting a few extra components in here to allow access to all of the address pins. I'll go through that in a later date. So the connection between the 5-volt Z80 pin, 3.3 volt Pico pins leads to slight complications, but they're not insurmountable. What I've got here is a resistor, pair of resistors to lower the voltage that comes from the 5 volts to something that's acceptable for the 3.3 volt system. So it's just a voltage divider. So up here on the address pins and the control pins, we've got a 5K resistor and a 10K resistor. So that drops the 5 volts down by a third to make it just about in spec at somewhere around 3.3 volts. For some reason that I'm not entirely sure of, the reason why I needed to use lower value resistors for the data pins, it might be that inside the ZX81 schematic there are already resistors on the data line. I'll have to double check. But anyway, 1K and 2K voltage divider seems to work okay. And so looking at the schematic can indeed see that there is a difference between the address pins and the data pins. The address pins go straight into the address bus, but the data pins on the edge connector are these D primes. And these D primes then go through a small resistor, and then on the other side, next to the Z80, they're pulled up to 5 volts through a large resistor. Now, if we're passing our 0 volts through a 5K resistor, then this 10K and the 5K that we're using will form a voltage divider and lead to a zero level showing up as 2.5 volts or thereabouts at the Z80. So I think that's what's happening. But if we use the 1K resistor, we get something closer to the spec of the 0 level. And then up here, I've just got a couple of switches as well. This switch connecting run to ground, does a reset, which is handy so that you don't have to constantly plug and unplug the Raspberry Pi Pico to reset it when you're trying to program it, go into program mode. And the other switch simply reboots the ZX81. So this is the connector that you'll need to connect the port at the back of your ZX81 to some electronics. So it comes as a slightly longer strip than this, as sort of solid plastic parts that need to cut off with a hacksaw, just shy of the first connectors here. You also have to take out one of the connectors here, and then what I usually do is take the bit that I've cut off the end and just jam it down in here, because that forms the key that needs that is used on the back of the ZX81 to make sure you've connected this in the right place. So you think it slides over the edge of the circuit board like that. Without that key, it could go anywhere. So that's that. The spacing of the connections is rather tight, but they're the right spacing for perf board. So just set through there and then just solder them onto the perf board, and then you've got your connector. Make sure you solder this the right way around, because if you get it the wrong way around, you'll have to put it on upside down. It's just not going to work. And it needs to be quite close to the bottom of the board because there's not much space. But yeah, you'll get the idea before you solder it. To check it on the board. You can't just use the connector on its own. You really have it soldered something, because you need the leverage quite apart from anything else to get it in and out of the board. They're a little stiff to start with, but if you just practice putting it on the end of your perf board there, it'll loosen it up a little bit, so it'll fit a bit better on your edge connector on your ZX81. I think that's about it, really. If you've not watched the videos of Ben Heck, I would suggest that you do so. But there's plenty of other prototyping videos. But Ben Heck's is really, really entertaining and really show you how to start connecting components on perf board. A couple of resources that are really useful when you're starting to connect 3 volts to 5 volts, 3.3 volts to 5 volts, is this application note by Microchip, which I found on this site, Hackaday, taking it to another level, making 3.3 volts speak with 5 volts. It just mentions this sheet. This link doesn't work, but it's application note DS41285A, and it really contains all the stuff that you need. First section is just about powering 3.3 volts, and then go down to page 9, page 10. Yeah, tip number 12, 5 volt to 3.3 volt resistor divider. So it's your 5 volt, your 3 volt. So these are the ones I've got, 5 volts and 5 kiloohms and 10 kiloohms for the address and control lines, and 2 kiloohms and 4 kiloohms for the data lines. It suggests putting in this capacitor as well. I haven't had to do that yet, but might try that in the future, depending on how things go. So obviously this steps down your 5 volt through the resistor divider to 3 volts, and I feel that it should just allow the 3.3 volts to communicate straight back with the 5 volts, because 3.3 volts should be above the +1 level for the 5 volt device. But I haven't got that far yet, but I think it should work. If not, then just put in a TTL level shifter or one of the other suggestions in this document, which I'll only need at the moment for the data line, because the address lines will be controlled by the Z80. Although I've been interfacing 3.3 and 5 volt chips with each other for a while, I have no training in this, so it's worthwhile, if you want to do this yourself, take a look at the datasheet. This is the Z80 family product specification handbook, February 1984, and it shows the input low and input high voltages, the output low and the output high voltages. This is on page 30 of this document. And for the RP 2040, we've got just the data sheet on page 616, and it's got the input voltages for 3.3 volts, which is the one we're running on, and it's got the output high and low voltages for 3.3 volts. I believe IOVDD is the just the 3.3 volts in our case. And taking a look at these voltages in the diagram, we can see that the output voltages from the RP2040 are well within spec for the input voltages of the Z80. And if we've got our resistor divider, then the output voltages of the Z80 are within spec for the input voltages of the 2040. So everything should be good, although we are sending high frequency signals, so we should expect some difficulty at least with capacitances, but we'll cross that bridge when we get to it. And so just to finish off, there's a quick look at the code that I've been using on the Pi Pico. The core of it is just to wait for a transition from high to low on the right pin of the Z80, and then just for timing's sake to wait for a high to low transition on the clock pin. I don't actually need this. I could just put in a timing wait if I wanted to, or a variety of things. So the clock pin isn't really needed, but just using it for now. I'm not actually using this Y register and this move command at the moment. I'm just playing around with them to see. I'm not very familiar with them, so that's why they're there. And same with all of this. It'll be for later when I'm trying to send data back to the Z80. And here's the main thing that we need, is to input all the pins in one command. That'll put it on the input shift register, and I've got auto push enabled, so I don't need to push. And then I just set an interrupt flag, and that interrupt flag then allows me to pick up the data in the C code on the main processor. So in the main C code, I've just got a buffer that's forming a first in, first out FIFO queue. And in my interrupt handler, after resetting the interrupt pin, it reads in the raw data from the FIFO, just does some shifting, pin shifting, bit shifting to get the address and data and the control pins. Then if it sees that the memory request pin is low and the write pin is low, and the address is for one of the AY39810 ports on the QS sound card, then it just pushes the address and the data to the FIFO queue, and the same if it finds the other address, the data address, it pushes that to the FIFO queue. You just push them to the queue so that it happens very quickly. If you didn't have a queue here, you might have one event happening whilst you're still processing the one before. And then outside the interrupt request, it just takes the values from the FIFO buffer and outputs them along the serial port, just in text at the moment. So nothing fancy. And that's great. Once this is written, you can just leave this program on the Pico and just interact with it through the USB. So yeah, the next step is just to alter the code on the Pico so that it can write back to the ZX81 as well. And then really it becomes very flexible, and the number of things that you can do with this are just going to amplify. I've already printed out the screen and saved a P file, things like that. One interesting thing to do would be to access the system variables on the fly as the ZX81 is running its code. You could see where the screen is, for example, or see where RAM top is. So yeah, quite a lot of fun that can be had once it's up and running.